All right, so welcome everyone. We'll get started. So there's no handout for this discussion because we didn't have any new content that we covered in the previous week. So what I'm going to do is very simple. I'm just going to walk you through the midterm. But before we get started, any questions about anything? So feel free to unmute yourselves. Feel free to ask me questions in chat. If you unmute yourself, that's slightly easier because I can listen to you. Otherwise, the chat, I have to change the window, but it's fine. You can do both. So actually, this one thing that I wanted to get started off with was an apology. So this apology is because of my delay in grading your assignments. So this is a week where I'll be grading all your past assignments and homeworks and this exam. So I was sick for a couple of weeks and had my dissertation due. So I was not able to do it, but I'll catch up on all of it this particular week. Okay. So you will have seen that Peter has already made an announcement about going to doing a project 2. So this project 2 is organized in 2 parts. The first part is a very simple exercise that you need to figure out what data set that you're going to use. And the second part will essentially end up you doing 2 particular analysis on whatever data set you choose. And these 2 analysis would be ANOVA and regression. And Peter is going to talk about it in the class starting this week. So you'll have ample amount of time to do these exercises. And these are very simple exercises. One thing that you can start kind of looking right now is what kind of data set would you be interested in? Okay, and when you look for a data set, you need to make sure that you can do a regression or an ANOVA on this. Okay, and these 2 terms will right now will sound alien to you, but it will become clear when Peter talks about it tomorrow on Thursday. Okay, any questions? Okay, in that case, I'm going to share my screen, turn my video off, and we'll talk about the exam. Okay. All right, so we'll get started with the first question. The first question essentially gives you indication of a doing an experiment where the expectation is that the heart disease will have lower concentration of protein. Right? So, and the thing is, it's already kind of mentioned what the hypothesis is for this particular experiment. So the first problem asks you a very simple problem, and that problem is the particular sample paired or unpaired? Okay. Any guesses what that is? So we'll this session I want to be a bit more interactive. So make sure feel to unmute yourselves and or write your answers on chat. But if I don't hear it, then I'll write it down what the answer is.
Would it be unpaired?
Okay, and why would that be?
Because the 2 data sets are not technically related to each other.
That's perfect, right? So this is an unpaired sample because just think about it. You cannot have a heart disease and the same person cannot have a non-heart disease, right? So it is an unpaired sample. But you cannot, can you do a t-test? Okay, so what would that answer be? So you're given the first QQ part is for the heart disease samples. The second QQ part is for the non-heart disease samples, right? So this looks okay. There's no problem with this QQ plot. So it looks normal. All the points kind of lie close to the QQ line, which is essentially a line to see. There are few deviations, but it's not like a big deviation that should worry you. However, this particular plot has some problematic point, and this point is completely deviating away. Okay. So in this case, it's kind of, you have very few samples, first of all. So this is deviating from normality. And hence, can't do a t-test because the normality assumption is violated. Okay, so we move on. So we are asked to do an appropriate test to test the speculation at a significance level of alpha. What would be first of all, what would be a good test? What would be your choice of test? So we have unpaired and we have non-normal samples. Okay, and you had access to the flow chart. Yeah, that's right. So Wilcoxon test, right? So you had access to the flow chart, which told you that you can do a Wilcoxon Mann-Whitney test. Okay, so given that, what is the null hypothesis? So the null is the simple protein concentration is same between heart disease and non-heart disease groups. Okay, given that you're asked to the alternate the direction, you're given what direction you're interested in, right? So the direction that you're interested in is the heart disease. People with heart disease have low concentration. Okay, and you don't have to believe those. It's just to give you an idea, you know, what you work with. So there are multiple ways to write these null and alternate hypotheses. As long as you are clearing, you're giving the right message, that's fine. Okay. Next, we're asked to calculate the p-value. So in order to calculate the p-value, we are going to do Wilcoxon Mann-Whitney test. And if you recall, we need to work with this strategy called the BISC. Okay. So Wilcoxon Mann-Whitney are signed rank sum test. So your rank is essentially given by the counting how many number of heart samples are lower, and this one is how many number of non-heart samples are lower. Okay, so we'll start off with this. So what we are going to do is I'm going to count for this particular value 20 how many number of samples are lower in this group. Okay, so only 8 and 10 are lower. So we have 2, 16, same thing, 2, 0, 7, nothing at all again, 9, just 1, right? And we're going to sum this. So this is going to be 5. Okay. We're going to repeat the same exercise on this side. So 50 is above all the values. So we get 5. 10 is above 2, 7, and 9. So that's 3. Then we have 75 above everything. 8 is just above 2 and 7. And 400 is above everything again. Okay. And if you sum this comes to 20. Okay. Let me make sure this is an overlap. So this is. So at this point, you can stop and you can do a sanity check. And that sanity check is that 5 plus 20 should be equal to n1 times n2, which is the number of samples. And in this case, the number of samples happen to be equal. So we are fine. Okay. This is your check. Okay, so we're there. The WS statistic is max of these two values, and that is 20. You need the only other quantity that you need is n1 is equal to n2 is equal to 5. Okay. Okay. What do we do next? So go to our table and are going to go to our table for Wilcox-Mann-Whitney. Our n is 5. Our n prime is also 5. We're going to look for a value of 20. So one check is the directional values are found by dividing the numbers of italics in half. So our p-value is going to be 0.5151 by 2. Okay, exactly. Don't need to calculate the bounds because you get the exact value. So, and this is going to be 0.075. Okay. And our test level is 0.05, which is since P is greater than alpha, we reject null. Sorry, we fail to reject null. In other words, you do not find evidence for the alternate. Any questions? Okay, so we will move to part E. Part E is saying that you did an error by calculating the 400 value that you saw. The particular value you saw here was actually an error, and hence you want basically it was a mistake, so you decide to remove this observation. Okay, and you're just removing it from non-heart disease sample. You want to repeat the same test as you did in the previous part, but without this observation. Now we're going to calculate the p-value again. So I'll try to again the new values here. So we have heart and not heart. These values remain the same. So these are 20, 16, 2, 7, and 9. And these values are 50, 10, 75, and 8. Okay, this 400 value is no longer perfect. So we'll repeat the same exercise. We'll count how many number of H are lower. So 50. So again, this more or less remains the same. So 50 has 5. This has 3. This has 5, and this has 2. Okay, and if you sum this up, then this comes around to be 15. Do the same exercise on this side, counting how many non-cells are lower. So for 20, you have 10 and 8, that's 2. 16, you have 10 and 8 again, that's 2. 0, 0, and 1. Right? Get 5 again. So check again, 5 plus 15 is equal to 5 times 4. This is n1 times n2. Okay, so now our n is 5, n dash is 4, our ws is 15. So we again go back to the table. So we have 5, this time we have 4, and we are looking for a value of 20. Okay, hold on, did I do a mistake? Okay, yeah. Okay. Any questions so far? Okay. So 5, 4, and sorry, this is not 20. Sorry, that was the mistake. That's why I got confused. So our value is 15, right? So the closest value is 16. And at 16, the p-value is going to be greater than 0.191. We're working in, so the 15 value will occur somewhere here, right? So this is definitely going to be greater than 0.91 by 2. Okay. So P is greater than 0.19 by 2, okay, which is essentially equal to 0.09. Okay, so at alpha equal to 0.05, your p-value is still greater than alpha, which is essentially again going to fail to reject. Okay, and hence there is no change in conclusion. So in some sense, you can see what really happened, right? So this 400 value was actually large value. You're doing a non-parametric test. So in some sense, you do not still just even if 400 is present, this is kind of outlier value. So even removing it will not actually is not going to kind of change your analysis, right? And that's because it's a non-parametric test. So uh, the exact value, the exact term is in some sense, if you have this particular extreme value, then that's not going to affect the conclusion that you make, just because it does not really depend on the exact value of this outlier, right? So you can remove the outlier and you can still have the same conclusion. Okay. All right. So what conditions do you need to verify before doing the test in part D? What's the foremost condition? Okay, that's fine. So that's perfect. So simple random sample. What other condition you need to satisfy? So each of these, that's right. Yeah, you need to be you need to have independence. Okay, so these are need to be simple random samples and they need to be independent, right? Okay, this is going to be important for one of the questions later on as well. Okay, so that was question one. Question two was about, again, another clinical test, but this time you're testing the weight loss and you're testing if this particular drug has an effect on the patient's cholesterol. So the clinician has measured the patient's cholesterol levels before and after administering the drug. Okay, and it remains same in the same patients, right? So this is the key here. It remains in being measured in the same patients. Okay, so first question, is this sample paired sample or paired sample? So it's fair enough. It's already given. It's paired, right? Okay. So now we are explicitly asked to do the t-test, and you want to decide whether it's going to be paired or unpaired. You already know it's going to be a paired t-test. Okay. So I'm going to calculate the difference, and I'm going to work with before minus after. The choice does not really matter. You can do after minus before as well. Okay, so I'm just going to write the differences. This is minus 10, this is minus 40, this is 5, this is minus 15, this is minus 15 again. Okay, this is going to call it D. So D bar is equal to minus 10 minus 40 plus 5 minus 15 minus 15. That's fine. So that's going to be minus 15, not wrong. Okay, so we'll go on to that before later. Let's write what the null is. Okay, so what's the null? So that's simple. There is no difference in the cholesterol levels between the two groups. Okay, and we all know what those groups are. And what's the alternate? So clearly it's a non-directional, so there is some difference. Okay. Now we have to calculate the p-value. So for p-value, we need the t-statistic, which is given by a d bar by the standard error. Okay. So we have some work to do here, and we'll do it in steps. So the first thing that you do is you want to calculate the standard error of d bar. I already told you, I already showed you the value of d bar is minus 15. The standard deviation, and to calculate the standard error of d bar, you need the standard deviation, right? And we know the formula for this. Okay. And this is the square root of this. Okay, so if you calculate this, and I'm going to essentially use the value that I've already calculated because you already have access to calculates, I'm assuming. Okay, and this value comes around to be 16.2. The standard error is 16.2 divided by square root of 5, and that's around 7.245. Okay, so if you calculate the t-statistic, this is going to be minus 15 by 7.245. And let me see what value this is because I have a wrong value here in front of me. So 15. Okay, so this is minus 2.07. Degrees of freedom is 5 minus 1, which is equal to 4. Okay. Okay, so we're going to calculate the p-value. And is there a question? Okay, so I'm going to calculate the p-value, and for p-value, you need to go back to the t-table. The degrees of freedom are 4. Your t-statistics is around 2. So just to make sure you got the value right, this is 2.07. Okay. Okay, so it's 2.07. So it will lie somewhere in here, right? And this is directional. So the p-value is 0.05, sorry, 0.10 and 0.05. Okay, and we're working in the two-dimensional with the multiply this value. Any questions so far? If you let me know. If you think your answer is different, let me know. I hope I've not done any calculation mistakes. So this is 0.10. Is definitely greater than 0.1, right? So what would be confusion? So at alpha, so what was it alpha? At alpha is 5, we failed to check. Okay, so question. Okay, so question. So there's a question. The question is asking me, will we get points for part B if we did not use the right t-test, but we got the right conclusion? Okay, let's see. Okay, does that mean you use the? So I'm assuming that means that if you use the unpaired t-test in this case, you have not done it, but maybe you'll get the same conclusion. It's fine, actually. It's nothing wrong doing that. The reason we do a paired t-test is because it's more powerful in some sense. It's fine because you're essentially, the reason it's more powerful is because you're essentially the variation that appears because of independent samples, right? And this one here is not an independent sample. So these two columns are dependent. Okay. Hence we work with this particular version of the standard deviation. I mean, sorry, this particular version of the standard error where we're actually calculating the standard error on D bar. If you ended up doing an unpaired version, where you do ST1 square plus ST2 square, you might get the same conclusion. There is, I mean, technically there is nothing wrong in doing it. It's just that the paired one is more sample. So I need to think you'll definitely get partial points. So don't worry about it. Okay. Let's see. Okay. All right. So okay. So the other one is finding the 95% CI. So this is again given by D bar plus T statistic and SE of D bar. The T statistic is 0.025. The T statistic is given by 8, sorry, degrees are 4. If you go back to your T table, 95% here, you're going to work with DF equal to 4, so that's 2.776. Okay, so this is 2.776. And if you plug in the values, I think get minus 36.1149 and 5.1148. You can also check these two comply. Fail to reject because 0 is contained in BCI. Any questions? It's not clear ones. Move to problem 3. Problem 3 essentially is uh, a test of association in some sense. And you're given that you are doing this experiment where you expect you have certain expectation. So we will write that expectation down in words, in numbers. So you can write it can be black. You can have, we have a total of so we have 40 students, 40 samples and 40 total. We expect 25% of 40 to have black eyes, so that's 10. We expect 50% of them to have black eyes, that's 10, 20, and 10 again. Okay, so these are your expected values. Okay, this is, so let me write this down in a different form. This is 40 and this is expected. Okay, this is half times, this is 1 by 4 times 40, half times 40, and 1 by 4 times 40. Okay. So to test the null hypothesis that the data agrees with the genetic model. You have a solution that this particular all genetics and so it's very simple. We are seeing that we have to test association false so your choice of test. Can you guys hear me? Oops. Are you guys able to hear me?
Yeah.
Okay. Thank you. Because it's showing me here. Okay, just making sure. Okay, let me ask this on chat. Okay. Okay, sorry. Okay, okay. My microphone is muted. Okay. Um, okay, are you able to hear me now? Okay, so sorry about this. These technology sometimes just plays a bit. Okay, all right, so we'll resume where I left off. And so we're going to calculate, we're going to talk about this particular problem where you're talking about genetics. So we start off with calculating the chi-square statistic, and it's very simple to calculate. You're already observing. So just write this down here for the sake of clarity. This is observed. This is 8. This is 22, and this is 10. Okay. So our chi-square is given by 8 minus 10 square by 10, 22 minus 20 square by 20, and 10 minus 10 square by 10. Okay. And if you calculate this statistic, I think this value comes around to be 0.6. Okay. So very simple value to calculate actually. The degrees of freedom that you have is, what's your degrees of freedom? Any guesses what the
Isn't
degree?
it 2?
Yeah, that's right. So this is 3 minus 1, which is 2. Okay, so we go to our chi-square table. And we go to 2. And looking for a value of 0.6, which is completely absent here, right? So P is definitely going to be greater than 0.2. Okay, so if P is definitely going to be greater than 0.2, then this is a bound actually, so you can just leave it there. So we will fail to reject the null at. Okay, right? Second problem, which I think some of you, I've not graded all of it, but I've started to grade and I've looked through some of the answers. I think some of you got confused here. So I'll talk about it in bit detail. So when we do a test, the probability of making a false positive in one test, right? It's 0.05. So what is the number of false positives? Number of false positives that are expected in 800 tests. Okay, that's very simple. So in each test, you have a probability.
Isn't it?
Yeah, go ahead.
I was just going to say, is it 40? Because you have 800 times the 0.05.
That's perfect. Yes. So this is 40. Okay. And what you're seeing here is these 38 students of them essentially ended up rejecting the null. Okay. So 38 of, so sorry. Just ignore that value here. So 38 is rejection expected. Sorry, 40 is what we expect. And we saw 38. So there's nothing surprising there, right? That's nothing surprising. And hence, the 38 students did not do a mistake, right? 38 students did not do any mistake. I mean, what I'm trying to say is these 38 students are in no sense any special. They're essentially this amount of expectation you have just because the way you're testing. Your threshold levels are set to 0.05. So you have the chance of making a 0.05 error just because randomly. And you're testing 800 of these hypotheses. So you have around 40 students that you know will reject just because the way you're testing, right? That's kind of your expectation. Okay. All right. Move on to problem 4. It's again a very simple problem. I'll write down the row and the sum totals before we talk about anything. This is 500, this is 280, and this is 220. What is the conditional probability that the drug D is effective? Sorry. That the drug D is effective if you have, if the patient has mutation N, right? This is essentially D and M, and probability that you get an M mutation.
Okay, so this is essentially equal to 20. Oh, sorry, 80. This is this number here, and probability of being having mutation M. So that's essentially 100, right? So essentially this is, I mean, I'm writing probability, but I'm writing numbers, but you can think of this as probability. So the 500 term essentially gets canceled. So this is 0.8. Second problem, which is the conditional probability that the drug D is effective given that a patient does not have a mutation in. So you have D and MC. Again, very simple. And this number is, you have drug D, but you do not have mutation, and the total number. Okay, this is equal to 0.5. Okay, now we are essentially testing if it's independent of whether or not the patient has mutation in. Okay, so this is a test of association, and hence we'll again do a chi-square test. So now it's very simple. There's no association between drug D and M. In other words, independent these observations are independent. The alternate is this. Okay, so there's no one way to, there's no one fast rule to write these null and non-directional hypothesis. You can just, this is my way of writing it. You can also use independence or any other similar analogy term that you want to use. We have to calculate the value, and for that we need the expected numbers. So these are expected numbers for, I'm going to say 100. Expected number for patient M and drug D. BC, okay, times 100 by 500. This is 20 times 100 by 500. This is 200 times 400 by 500. This is 200 times 400 by 500. You can, I'll just write down the formula and the final. So this is like E minus 56 squared plus 56 plus 20 minus 44 squared 44 plus 200 minus 224 squared and 200 minus 76 squared 176. Okay, and for the because I think is okay. Your piece of feed is 2 minus 1 times 2 minus 1. And if you find out this on your because it's definitely going to be lesser than 0.4. So let's do that. Fairly and you have a very so you'll not find anywhere, right? So this is your before. So the P is, and this one is already on. So, no, hence we project. Just a collection of simple problems to check if you understood what the interpretation of p-value is in some sense. Okay, so the first problem talks about the effectiveness of a new cholesterol reducing drug, and essentially in the first sample you're given 20 patients who received drug and placebo. The p-value is 0.25. Actually, it's a very large p-value, so going to not we will fail to reject the null. Now there's another scientist. We are essentially using the same drug But in this study, we have 150 samples, right? So we have more number of patients. And for this, the p-value is 0.0002, which is by all means significant. So why, right? So what is in this? Essentially using the only difference that you do is the patients themselves are different and the number of patients are different, right? So the sample size, right? Size causes larger sample size in the larger case leads to physical. In the first study, because the sample size was small, we are not given the effect size. So we are not given how much are we really seeing. But what this essentially being in some sense is significant, and the reason it's turning out to be significant is just because your sample size is larger in the second case. Okay, any question there? So if looking at the experiment, I've seen that the effect is because one of the reasons it could happen is because your sample size is small. So if you increase the sample size, your p-value is going to be significant. You're testing for two drugs, and the clinician is deciding if the patients who have taken drug A are much more likely to develop dementia than the patients who have taken drug B. Okay, and there's one important catch is she already the way she's prescribing it, she's prescribing for patients based on their is that the clinician that drug increases. What are your views on it? Anyone wants to take a hit on this problem? What conclusion do you draw from such an experiment? Any guesses, views on what's wrong, what's not right? All right, let's see. Yeah, perfect. So I think, yeah, perfect. So I think all of you are getting it. So it's not a simple example, right? It's not a simple example because and as these two groups, so group one and group two, are essentially the is rather. All right, so 1, 2, 3, and the problem is to the partner first the mean height of the bond was is 0.93. Next, testing the which is your value 40 value of 0.93 is definitely greater than 0.31. Okay. And hypothesis one is in A is greater than in B, and this is height. And in the second, you're testing the same for sugar concentration. Okay. So would you agree with this conclusion that if you're getting the p-value for this to be 0.93 and this 0.31, there is probably more evidence for supporting the statement that the concentrations are the same? Okay. Okay, and why would that be? So why would it be no? So we don't explain. So let me write this down. So I don't agree with this, but now I need the reasoning. And why would that be? Sorry. Okay. Anyone wants to take a guess? So this is essentially what is a p-value, right? So p-value is does not mean that it's not the so it's not the probability of h naught being true, right? It's not telling you whether the null hypothesis is true or not. That's not the definition of p-value. So this interpretation, this problem with this interpretation of what the farmer is drawing. Okay, so the interpretation is of p-value is what is the probability that you'll see an output as extreme as what you're seeing, given that the null hypothesis is true. Okay, so hence you can't compare the p-values of two hypotheses. Okay, does that make sense? I mean, when I say that, it's in this setting. It's in this setting where the hypotheses are on different categories. Okay, with that, I'm done. I'll take any questions you have, any concerns. Solutions will be made available online, but if you have any questions, let me know. Okay. Sorry about the technical issues today. This machine seems to have some issues. Okay, any questions? Okay, in that case, have a good week, and I'll grade the exams and you'll have your scores by the end of this week. Okay, and make sure you read the announcement about the project. Okay, cool. Have a good one.
Thank you.
Thank you.